All right, so stepping forward here, we're going to take a look at congruent triangles and similar triangles. We'll start off with congruent. Two figures are congruent if they are the same shape and the same size. Okay, so the symbol for congruency is an equal sign with a tilde over top. Now, when two triangles are congruent, that means that 6 things are true. That means that they'll have 3 pairs of equal side lengths. So in this case, that would be something like A and C are an equal side length to D and F, and C and B are an equal side length to F and, whoops, there should be a G there. And A and B are equal side lengths to D and G down here. Also, what's true is that their angles are going to be equal. So that means that angle A here is equal to angle D, angle C equal to angle F, angle B equal to angle G. Now you can see in here there are different symbols. So this triple line means that it's the same side length as this triple line. This single line, same side length as this single line, and likewise for the double line. Same thing with our angles, where the single lined angle over here is the same is the same angle as angle D. The same angle, double bar right inside here, is the same as angle F. So hopefully here you're able to recognize, you're able to take away from here the symbols that represent the same side lengths or the same angles here. Now, moving forward, let's take a look and let's complete the congruency statement. So again, you see this symbol that we just wrote up above. This means congruent. Now, SAT, that's one triangle. So the triangle, there's our triangle symbol. The triangle SAT, that's right here, starts at S, then goes to A, and then T, will be congruent to this other triangle, and we need to label it in the same order. So here we have the angle S, that's our first one, and that is that's our single bar right here. So angle S is equal to angle F. So that means triangle SAT will be congruent to triangle F. And then we have our right angle A here. So we need to find our right angle C. So F, C, and then the last is the double bar, that's B. So triangle SAT is congruent to triangle FCB. All right, now we'll continue forward and we'll use this same pattern. Okay, so triangle BCD. So we start with B, that's the triple bar, meaning we need to go to the N down here. So is congruent to triangle N, and then it goes from B to C. C is the double bar, so N to M, N, M, and then from C to D here, M to D as well, N, M, D. And lastly, we'll work with GHK. All right, so we start with G. That's going to be the same angle here for our other one. Then we went to angle H, which has a single bar, so we'll go to angle T, again a single bar, G, T, and our last one is angle K. So this is how we write out our congruency statements. And I realize there's a question mark in the middle. The complete, say, for example, this third one, the complete congruency statement would be triangle GHK is congruent to triangle GTK. Fantastic. Now we'll push on forward. If we're looking to prove or to show, to demonstrate that triangles are congruent, we do not necessarily need to double check that every single angle is equal, that every single side length is equal. Because as long as a few things are equal, they're going to require the other ones to be equal as well. So if we double check, if all of the side lengths are say we have a pair of side lengths that are equal, then we have another pair that are equal, and a third pair that are equal, that means that their angles are also going to be equal. We don't need to go in and double check that the angles are equal. Okay, so that's called a side condition. Now, otherwise, we can have a side angle side. And in this case, the angle must be contained within the sides. So let's say we have a side here and a side here that are equal, and then we have a pair of sides here and here that are equal. If this internal angle, this inside angle is equal, that's enough. But instead, let's say we have this angle is equal. That's not enough to prove congruency. The angle must be contained within our two sides. Now, likewise, and again, that one's called side angle side congruency. And likewise with angle side angle, we must have the side contained within the angles. So let's say we have one angle here, a pair of angles here that are the same, and a pair of angles here that are the same. If this internal side length is also the same, that's enough to prove congruency, but not so for the others. We need to have that internal side here. So we're going to work with some examples here. We'll prove congruency, and we need to use one of these three strategies. We either have side, 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 angle, side, or angle, side, angle. So let's double check inside here. So I see an angle here that is the same. So I'll even draw in the angle there. And then I see a side length right here, side length 5, and it's right beside this angle, and that's important. So that's nice and useful. We'll give that its symbol for an equal side length. And then I have another side length down here. The 7 is equal to this other side length. And we see this angle is in between the 5 and the 7 for both triangles. That's what we need. Since the angle is in between, we have here side, angle, side congruency. All right, now we'll jump into the pair of triangles for example B. Here we have let me see here, we have a side length 12 and 12. Those are equal. I have an angle opposite them, that's angle C, and those are equal. And then I have an ABD. So what can we do in here? Well, we don't know that D is equal to angle B, and we don't necessarily know that the internal angles here are equal. But what we do know is that this side length, AC, is shared between the two triangles. Since it's shared between the two triangles, what I'm sitting with here is our two sides here and here, two sides here and here. And if our two sides are equal and we happen to have a right triangle for both, right? We have a right triangle. That means the third side length will also be equal, right? Through our Pythagorean theorem, a squared plus b squared equals c squared. Therefore, we have side, side, side congruency here. And we can push on forward. Let's take a look now, not necessarily with congruent triangles, but with similar triangles. So two figures are similar if they are the same shape, but different. And really, they can be different or the same. So they can be any sizes, right? Because if it's different, then it's not congruent, but it is similar. And if they're the same, then it is congruent, and it's also similar. Congruent triangles are an example of similar triangles in itself. So the symbol for similarity is this here. That's the tilde. Now, when two triangles are similar, there are 4 facts that are going to be true. Number 1, the ratio of corresponding sides will be equal, meaning AB over DE, right here. So the pair of similar sides will be equal if we divide AB by DE. That's going to give us the same ratio as if we take BC and divide it by EF. And that's also going to give us the same ratio as if we take AC and divide it by DF in here. Okay, now also what's going to be true in here are the corresponding angles will be equal. They won't be, we're not looking at a ratio here for the angles. We're looking and we're seeing that the angles themselves will be exactly equal. So angle A will be equal to angle D. Angle B will be equal here to angle E. And angle C will be equal to angle F. Now, again, just like with our congruent triangles, if we're needing to prove or show or demonstrate that triangles are equal, sorry about this. I'm jumping all over the place. Let's try and keep this zoom the same here. There we are. If we need to prove that the triangles are similar, we do not need to show all four things are true. We don't need to show that the sides are, that the ratios are equal. We don't need to show that our angles are equal. So we can get in here. There are certain combinations, just like before, that are enough to show that they're similar. Side, side, side. If the corresponding sides, oh my goodness, I'm sorry about this. I hope this isn't giving you a headache to watch this. If our corresponding sides of two triangles are proportional, then the triangles are similar. And that means if here BA, which equals 4, and JG, which equals 8. So that means 4 over 8 equals 1 over 2. Right? That's our first ratio. If that's the same as 5 over 10, let's check it out. 5 over 10, we can reduce that to 1 over 2. Fantastic. And then if we can double check this last one, 6 over 12. 6 over 12 equals 1 over 2. Good. So we see this consistent ratio. That's enough to show similarity, side, 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 similarity. Okay, and then we can go in and we can check. Here we only need two angles. We don't need the third angle. And the reasoning for that is that if two pairs of internal angles are the same, oops, and I've colored those incorrectly, haven't I? 45 and 45. If two pairs of internal angles are the same, then the third angle will also be the same. We can find that from the sum of internal angles of a triangle. It always equals 180 degrees. If that's the case, angle, angle, two angles are all we need to show similarity. And lastly, just like before, side, angle, side. So if we have two pairs of similar sides, so here say we have 3 over 6 again, 3 over 6 equals 1 over 2. And then I can double check. And we need to stay consistent with our order. If my side length from this triangle was in my numerator, right, was in my numerator before, then the side length of my next one also needs to be in my numerator. So that's 2 over 4 equals 1 over 2. Fantastic. Those have a consistent ratio. And then we just need to double check, do we have an angle here contained within that is the same? In this case, yes, we do. B and J are similar. Therefore, we're sitting with side, angle, side. Again, it must be a contained angle like before. Okay, so we'll double check with some examples down here. In order to solve for side lengths, for missing side lengths in similar triangles, we create what we call a scale factor by stating the corresponding ratios, the ratios of the corresponding sides. So this, what we have in here circled, this 1/2 and 1/2 up here, that's what we call our scale ratio. So for the first pair of triangles, our scale ratio is 1/2. For a second set of triangles, our scale ratio is also 1/2. It will not always be 1/2, but sometimes it is. So we'll work here with example A. And we'll take advantage of a few patterns that you would have learned in grade 10. So in particular here, we're going to handle this double arrow. That double arrow indicates parallel, right? So we have two sides that are parallel. If we have two parallel sides here, we can use our Z pattern to see that angles Q and S are equal. Angle Q equals angle S. And likewise, we can use another Z pattern on the other side to see that angles P and T are also equal. If we have two pairs of equal angles, then we have angle-angle similarity. And from there, we can use the fact that they're similar to recognize that we're going to have a scale factor. So let's make our scale factor. Our scale factor will equal one side divided by its similar side. So in this case, I see side QR and side RS are similar here. I have 6 over 3. So we'll take the big triangle divided by the smaller triangle. We don't need to. We could do that in the other order. We could do the small triangle divided by the big triangle. We just need to stay consistent throughout the problem with how we handle that. So here we're going to be working exactly with our scale factor. That's 6 over 3. I can reduce that to equal 2. So if my scale factor is 2, I need to find the unknown side lengths. And that means here I need to find the side length PR. In this case, I'm working with PR. The similar side is side length RT. So RT is the big one, so that's going to be in my numerator. That's side length 5 divided by PR. Oops, PR. And I know my scale factor is 2, right? So I can take this scale factor and I can use it moving forward. So my scale factor equals the big triangle side divided by the small triangle side. Now I can rearrange this. I can multiply both sides by PR, and I can divide both sides, let's see here, by 2. So multiply by PR, multiply by PR to give me 5 equals 2 PR, and I want to isolate for that PR, so I divide both sides by 2. Oops. Leaving me with PR equals 5 over 2. Fantastic. So there is my one unknown side. My other unknown side is this ST. The similar side is the parallel side. That's side length 4. So again, I can use my scale factor. 2 equals the big triangle side, so that's side length X, divided by the small triangle side, so that's 4 centimeters. I can rearrange this, multiply both sides by 4. Leaving me with X equals 8. Therefore, my X equals 8 centimeters. Centimeters is my units in there. That's how we can use the knowledge that our triangles are similar in order to create a scale factor and use that scale factor to find unknown side lengths. We'll go over one more example down here. Example B. In this case, we need to look for the similar triangles. I see triangle ACB will have the exact same angles through F pattern as AED, right? So angles, so the first triangle is all the way around. Second triangle is the smaller triangle in here. They both share the same angle A. And through an F pattern here, right, I see an F pattern here and here through the parallel sides that are 4 centimeters and 10 centimeters. Then I see that angle E equals angle C. And again, through an F pattern here on the other side, angle D equals angle B. Now, I didn't need all 3 of those angles. I just needed 2 of them to say that I have angle-angle similarity again. And since I have this angle-angle similarity, I can use this just in the same way that I used the other scale factor in order to find my similar side length. So in this case, AE would be similar to AC, and side length AD would be similar to AB. Right? Whereas DE, this third side length, will be similar to BC. So we'll use that information as we go forward here. Well, first we'll find our scale factor. Again, we'll go the big triangle on side length on top. So we'll use the one pair that we already know. That's a 4 centimeters and 10 centimeters. So my scale factor tells us that we're working with scale factor equals, 10 divided by 4. I can reduce that 5 over 2. And I can use this scale factor in the same way I did in the previous problem. I can use this scale factor to find my unknown side lengths. And again, those unknown side lengths here are side lengths AB as we go forward. You should be able to handle that on your own. I'm not going to finish that one because it's the exact same process as above. If you get stumped, you can certainly reach out.